presentation?
Yes, yes, yes.
Yes, it is
Yes,
visible.
sir.
Yeah, it's visible.
Yes, sir. We are able to see.
Somehow, I think there is some. This thing. My camera is not starting. Just hold on. Hold on. I got it.
Sir, but we are hearing your voice.
Okay. Okay. Fine.
Yeah.
Now
Now
it's
it's
good.
Now
okay.
we are able
Yeah.
to see you.
Yes.
Yeah.
Right. So, good evening to all of you, and I would like to thank Concrete Engineers for having given me this opportunity to present on this topic. It's really an honor uh, to be presenting to all the distinguished guests. It's much long after COVID that I am presenting online this way. Otherwise, it had become a physical, so kind of it is becoming like a nostalgia where during COVID time we had a lot of presentations. One good thing about COVID was, we had a lot of presentations because people used to not go for work, and a lot of knowledge sharing happened that time, and a lot of new things we got to learn. Many of us have learned a lot of new things. So something that reminds me back of those days. Anyways, starting with my presentation, this is perform high performance concrete uh, proportioning with ultrafine minerals. And I would like to take you through the presentation through all these contents. So first, what we would like to say is the water cement ratio. Why exactly the strength of concrete, depends on the water cement ratio, uh, and the history about it. How people realized, how concrete workers here realized that the strength of concrete is dependent on the water cement ratio. Just hold on. So there were people like Abrams, Farret, then Bolomi. All these people worked on the strength of concrete. They did a lot of research and came up with uh, this equations through which you could predict the strength of concrete, and the inputs, whatever were the most significant input variables, they gave their mathematical models. Or if you see, most of these guys who worked on this concrete strength models, most of them were French. And why these French people were mathematically working on that, we will try to see that also in the in this presentation. After that, we'll see why do these laws work. uh, in in real life, we behave based on what, however the law is made. If we are asked to, if the law is to drive on the left side of the road, we drive on the left side of the road because the law is that way. But in science, it is the other way around. The laws are made based on the actual performance of the material. The materials do not behave as per the law, but the laws are made as per the behavior of materials, or as per the physical real life scenarios. Then why do we get better rheology with ultrafines? When we use ultrafine, why do we get better workability, lesser what do you say, stickiness, uh, a lower viscosity? And then how to proportion concrete mixes with ultrafine? Of course, there is IS method, there is ACI method, but they have got limitations. Uh, right now, the IS code or ACI method of mix design, does not give a good uh, and a reliable method of designing a concrete mix with ultrafine minerals. So we will try to see what are the things to work around for proportioning concrete with ultrafine minerals. Then we'll talk about the ultrafine based mixes advantages, and we'll see the real life case studies, where ultrafine material has been used and to a very good advantage. So let us start with the water cement ratio law. So in the year 1919, Duff Abrams, English guy, uh, he did a lot of work. And there were a lot of inputs. The strength was the output, and they tried to find out how to increase the strength, and through lot of research he came across this relation that the strength of concrete is inversely proportional to water cement ratio. Now, many people till today they feel that the strength of concrete is dependent on the cement content. The more the cement content, the higher the strength. Um, but in the year 1919, there was this person who focused on the strength of concrete, and he tested the strength of concrete by varying all the possible variables. And he said the only thing that affects the strength of concrete is the water cement ratio. Believe me, I have tried to actually challenge this, law. I have tried to, change the aggregate proportions, because some people say that increasing 20 aggregate, some people you'll see that they say 20 aggregate, if you increase, you will get higher strength. Some people say if you increase 10 you get higher strength. Some people, talk about other things. So I have done, personally, I've tried to check whether this is actually universally applicable. And till today, I have not been able to, overcome this equation. And every time I end up getting that the highest significant factor for strength is the water cement ratio. Of course, now since in the year 1919, the only thing that they were using was cement. They never used fly ash or slag as replacement. So Duff Abrams did not test percentage fly ash, percentage slag, or percentage ultrafine kind of a material with this. So the second most significant factor for predicting, or on which the strength depends, is the additive materials that you add into it. It could be fly ash. So if you are replacing more amount of fly ash, the strength will be lesser for the same water cement ratio. But economically, for getting the same strength with fly ash and OPC, you will get a better performance with fly ash, because fly ash being much cheaper. Or for durability purposes, there could be other equations models. So for fly ash, same percentage of fly ash, even though the strength will be lesser, but you will get a better performance in other things like the heat of hydration and so on. So uh, if you see the strength, the biggest factor is the water cement ratio, and many people have worked around it. No one has been able to negate whatever was established in 1919. And if you see during that time, somewhere around 20 years after that, somewhere in 1920s, the late 1920s, there were two people from France, the Ferret and the Bolomy. Uh, these guys also were working on the strength modeling. And if you see historically, the American engineers, the English engineers, they never were so much bent towards mathematics. They all did their works on gut feeling, whatever they did, gut feeling. So there are cases where, bridge construction used to happen in US, in UK, and they used to never design the structures. If you see the traditional engineering, there was no calculation. People used to just, there used to be just, they used to start constructing the buildings, block after block, and the building used to stand, or else it used to fall down. And American engineers and the British engineers, they were able to again make very good structures, very strong structures, which are still standing till today, without any calculation. It was just based on thumb rules and a very huge factor of safety. So that is how it happened. But during that time, the French engineers, they were very much fond of mathematical calculations and modeling and finding out, the load at the different parts of the structures, and they used to construct the bridges. And most of the French bridges used to fall down, uh, and slowly they realized. And what has happened after that is the entire world realized the power of the mathematical modeling, and they started incorporating that into design. And that is the reason why we are able to now make more structures with the same amount of cement, with the same amount of materials, and very thin and slender structures. So mathematical models did not help initially, but later on they really helped us. And if you see, most of the equations, the oldest equations that still work today are from France, but that did not happen in this water cement issue, because Farrett and Bolomy, they came much later. And some companies today do follow the Bolomy's equation. I had met a person from Lafarge. They used to calculate the strength, they used to predict the strength based on the Bolomy's equation. And if you see these equations also, even though there would be no water cement ratio per se, uh, which would be predicting the strength, but somehow or the other, it leads to the same thing. There is cement at the numerator and there is water in the denominator. So this is the Ferret's equation, where this is the VC is the volume of cement, VW is the volume of water, VA is the volume of air. And this was the equation that Farrett gave. Similarly, Bolomy gave this equation where cement divided by W. Cement is the weight of cement, W is the weight of water. And these factors had to be calibrated based on so this was the factor that he calibrated based on whatever material he had. And then Francois Larard, a French engineer again, who's still alive, he tried to, he did around a couple of trials with different cement ratios. And what he did was he plotted the equation as per the Farrett's formula, as per the Bolomy's formula, and as per the Abrams formula for the same set of water cement ratio or same set of mixes and their strength. And if you see, all these equations actually fit the curve very well. Uh, the only thing that he did was, if you see, he changed these numbers. So to fit this equation as per his data, he only changed these numbers. And this was how he did the curve fitting. And just by changing these numbers slightly, calibrating it, he was able to, fit the curve. And if you see, it gives you a very good, data fitting. I don't, no matter which equation you follow. Now, why do these laws work? Just excuse me a moment, for a moment, please. I need to take this call. It's okay, fine. Thank you. So, why do these laws work? As I told you, as humans, we follow the law because the law is made that way. But in the world of science, it happens the other way around. So the laws work because the materials behave that way. And why does this happen? Let's see that. So let us say you have some cement, or maybe let us say you don't have cement, you have clay, and you mix water into the clay, and you make a slurry or a paste out of that clay, and you have got a cube made out of that clay, right? And then what you do is you take a similar kind of clay, you put similar amount of water, but what you do is you add in more amount of water. And similarly, the third case you take, and in the same clay you add even more amount of water. If you see, the difference between these three, visually would be, these three pastes would be that the third one, where the water content is very high, would be a little lighter. It would be a little less denser. The third one, it would be light in color. The first one would be much darker in color. And once this clay paste dries up, or when it starts developing the strength, it will start showing that, the first mix is more stiffer, and the third mix is more weaker, because the water molecules between the clay particles, they evaporate out during the course of hardening. And these clay particles, they adjust themselves to incorporate even the water particles amongst them. And you get a very porous kind of a structure where the water evaporates. And if you see mathematically, per unit volume, per unit volume of all these three materials, the water content would be highest in number three per unit volume. Water content would be highest, and the clay material or the strength giving material, the solid material, would be the lowest in number three. And the exactly opposite would be number one, where the cement or the clay content would be the highest and the water content would be the lowest. So this would be a more stiffer kind of a mix, and when it dries up, this would give you a higher strength, right? Now, when you add stone pieces into it, so stone is nothing but let us say aggregate, and we all know aggregates are much more stronger than any clay paste, right? So when I add aggregate, the same proportion of aggregate in all these three clay mixtures, clay and water mixtures, I would not get the same strength even though I'm putting the same aggregate, the stronger material in all these three. The reason being, the strength of a material is the strength of the weakest material inside it. If I've got a mixture of materials, the strength of the composite material would be the strength of the weakest material. And even though the first paste was the strongest, even when I have added much more stronger material into it, the strength of the composite material, the mixture of this composite material, would still depend on the weakest material inside this, and that is the clay. And since across all these three, the weakest material is strong and uh, hold on, please. Hello, boss. I am in a meeting. Can I call you after some time, please? It will take me 1 hour. Yeah, I'm sorry. Sorry for that. So this the strength, is dependent on the strength of the weakest material, and the weakest material is the clay, right? Now same thing happens in concrete. We all feel that the cement paste is stronger than aggregates somehow, or we don't know what exactly happens. The weakest aggregate, if you measure the strength, would be 150 MPa, whereas the highest strength a cement paste can get is somewhere around 100 MPa, which can be made with an acceptable amount of workability. That is 0.15 water cement ratio, even with the admixtures. So that would give you the maximum of 100 MPa. The reason being, the strength of that material is just 100 MPa at 0.15 water cement ratio. And if you see Adam Neville, the father of concrete technology, the modern concrete technology, he has reported in his book that he tried to make concrete with 0.08 water cement ratio. And he was able, and he compacted the cement paste, just the cement paste, at 0.08 water cement ratio, which was not workable at all. But he compacted it with pressure and vibration, and he got a strength of 235 MPa, but at a water cement ratio of 0.08. So that would be somewhere around 2000 kgs of cement. When you work out, when you do the reverse working, that would be 2000 kgs of cement per cubic meter, more than 2000. Uh, and that is what he got, when making a concrete or a cement paste at a very low water cement ratio. So don't expect that you will get a strength higher than 100 MPa with the same materials that you are using. Now, there is some other research also that has been done, and this photo is a very interesting one. This is published by the Federal Highway Research Institute, wherein they have taken this microscopic picture of concrete with a water cement ratio of 0.6 after 6 months. And this was the concrete which was at the port, constantly in touch with water. So no one can say that the curing was not done over there. Okay, there was natural curing happening for 6 months with a water cement ratio of 0.5. Now the interesting thing that you see after 6 months is there is still unhydrated cement particle in the left side of the picture. If you see, this is unhydrated cement particle. Around it, the dark color material is the hydrated cement paste, that is nothing but CSH, the calcium silicate hydrate gel. On the right hand side of the picture, if you see, it is an aggregate on the right side of the picture. This is a sand particle under the microscope, and surrounding it again is the CSH, the calcium silicate hydrate. Now, this test is nano indentation test, and a nano indentation test, they measure the strength of that material at that small point. So it's a needle with a very small diameter. Actually, it's a triangular in shape. And what they do is they prick this at different points inside the concrete and measure the strength of those points. And if you see in the unhydrated cement particle, when they pricked, the number that they got is 105, 107, 102, and so on. Whereas inside the CSH paste, they were getting a number of 17, 13, 23, almost 7 to 10 times more than the the CSH that you got the strength in unhydrated cement particle. And if you see on the other side, the aggregate gave a strength of 126, 110, 123. And similarly in the CSH, if you see, it is 16, 18, 23. So these were the numbers that they got, while measuring the strength. Now, the reason you get higher strength with low water cement ratio is because, now if you see, there are many things, there are many data you get from this picture, from this study. First is, cement does not hydrate fully even if the water cement ratio is 0.5. Many people say that for full hydration of cement you require a water cement ratio of 0.27. That may not be true, because the cement particle is much bigger in size, even though it seems very finer, but the water is able to hydrate only the surface of the cement particle and is not able to go inside and hydrate the full cement. Second, the strength of unhydrated cement particle is much more than the strength of the hydrated cement paste. The aggregate also is much more stronger, and aggregate and the unhydrated cement particle are almost the same strength. So basically, when you are getting higher strength at a lower water cement ratio, expect that at low water cement ratio, the CSH gel formation will be much, much less as compared to water cement ratio at a higher level. When the water cement ratio is 0.5, you will have more of CSH paste. And when the water cement ratio is 0.2, the CSH gel would be much more smaller. And a correlation is that the higher amount of unhydrated cement particles inside the concrete, the more is the strength. The higher amount of unhydrated cement particle in the concrete, the more is the strength. Now, many people would say that that's not what they have read in theory. They have read in theory that the more the hydration of cement, the higher is the strength, right? So there is the wrong interpretation of that statement. And I would like to give this example. Many people will interpret this statement, what you see on the slide. I didn't say he slapped his wife. There are many different interpretations of this statement. So the first statement is, I didn't say he slapped his wife. The first interpretation is, I didn't say. Someone else said. Uh, uh, Rahul said, or Lakshmi said that he hit his wife. The second interpretation is, I didn't say he slapped his wife. I didn't do anything. I didn't do anything. I didn't. Where you are stressing on the didn't. I didn't say he slapped his wife. The third interpretation is, I didn't say he slapped his wife. I actually wrote it down. Or I was just thinking about it. Then the fourth interpretation is, I didn't say he slapped his wife. I said she slapped his wife, or that other person slapped his wife. He is a good person. He does not slap his wife. It is actually some other person who slapped his wife. The fifth interpretation is, I didn't say he slapped his wife, but he, kicked his wife, or he kissed his wife, or did something else. He didn't slap, but he did something else. I didn't say he slapped his own wife. I said he slapped someone else's wife. And the last impression is again, he didn't slap his wife, he slapped some other, he slapped his friend or something. So if you see, any statement has to be always seen, a scientific statement has to be seen in full and it has to be understood. Even though the interpretations can be many. And when I say this, the interpretation that the hydration of cement more gives you higher strength is also correct, and the more amount of unhyded cement particles is also correct at the same time. So what I try to mean is the cement particle, each cement particle must hydrate. There should be no cement particle which not even the surface is hydrating. Every cement particle's surface must hydrate, and for which you require a good quality admixture so that all the cement particles, they are away from each other, they are not bond with each other, so that the surface does not get exposed to water for hydration. If that case is there, these lumps of cement will give you lower strength. So the cement particles should disperse. All the cement particles must come in contact with water, and all the cement particles must hydrate. But to get higher strength, each cement particle should not hydrate fully. Only the surface should hydrate, and it may bond a CSH gel. It may form a CSH gel and lock with the other cement particles, but the internal particles should be intact, and that is how you will get a high strength if you are looking for high strength. Also, yours truly, in his book Practical Concrete Mix Design, uh, has come up with this formula for predicting the strength of concrete. And this is nothing but the water cement ratio. WC is the water cement ratio. FT is the strength of concrete that you want to find out, right? So, and CS is the strength of cement. So, many a times people come across a situation where they don't know the strength of the cement. So, how do you use this equation? Just do a trial with any water cement ratio, 0.5 water cement ratio you take, you make the concrete, find out its strength, and calibrate this equation. You will need to calibrate this equation. And how do you calibrate this equation? You put the water cement ratio as 0.5, and in the place of FT, just put the strength of concrete that you got, right? So let us say if you got with zero point 0.5 water cement ratio, you got a strength of 25 MPa. So put 25 over here, zero point 0.5 over here, and find out the value of CS. CS is the strength of cement. Now, once you have found out the strength of cement, you can now predict the strength for other water cement ratios. So you can put this, plug in the CS value at this respective places, and whatever strength you want, you can either put, let us say you want 35, you put the 35, and let us say the cement strength you get is 58, you put 58 all these places, then you'll be able to get what water cement ratio you require to get the strength of 35, and so on. Or you can do vice versa. For the water cement ratio and that cement strength, you can calculate what is the strength you will get. So this equation, is what I have developed based on my years of study, and kind of it works well, and it works even for, let us say, 3 day strength. So if you want a 3 day strength, so let us say you put a water cement ratio of 0.5, you again at 3 days, whatever strength you get, you put that strength over here. So CS would be the strength of cement in 3 days. So if you want a different strength for the same set of materials in 3 days, so you just plug in that strength for 3 days and plug in the strength for cement for 3 days, and you will get the water cement ratio. So this is how this equation works. Now, you know, ultrafine materials, they basically give you many advantages. The first advantage is it gives you a better rheology. The ultrafine materials gives you better rheology as compared to materials without ultrafine. And this is what has happened in the modern science. So, as I told you, Francois du Larard, he has done a lot of studies in particle packing. and he has burst some of the myths in concrete technology. So the first myth in concrete technology is uniform gradation of aggregates give you good particle packing, which is absolutely wrong. What is uniform particle packing? In uniform particle packing, what happens is if you have got 20 aggregate, the assumption was that the voids are 10 in diameter, half the size. So if you see all the sieves that you use for sieve analysis of the aggregates are half in size, 20, then 10. Below 10 sieve is 4.75, which is very close to 5. Below 4.75 is 2.36, and so on. All these are half. And the proportions of these materials are, in such a way that, they have, each material has to be there. And many people get, annoyed when they see some middle part of the material is missing. But if you see, without gap grading, you will not be making the concrete even today. The concrete that you are making today is actually gap graded. It may not be 20 and sand that you do is called gap graded, but 10 and sand, 10 aggregate and sand, you see the middle portion is most of the time missing, 4.75, even if it is a river sand. So, and if you are making a good river sand, which you call it, where 4.75 particle also is available, 2.36 particles also are available in good quantity, in that case, the mix would turn out very harsh and porous. So, a good sand is the one where the top sizes are missing. 4.75 is missing, 2.36 is much lesser, and 10 aggregate is more towards 10 size. So when you're putting 20, 10, and sand, most of the middle sized particles between 10 and sand is missing, and that is the reason why you get good concrete. So in this study, if you see D2 by D1, this is the ratio of bigger size aggregate to smaller size aggregate. So 0.625. So if let us say 20 was the size of the bigger aggregate, then the size of smaller aggregate is 12.5. So he makes 20 aggregate and 12.5 aggregate at different percentages of ratio. So 20% of 20 80% of 12.5 aggregate, and that gave this kind of this much particle packing. At 40% it gave this much. So this mixture, at different percentages from 0 to 100, it means the percentage of 20 So as you keep on going from left to right, the percentage of 20 is increasing, right? So this is what study he did with 20 and 12.5, then 20 and 10. This is 20 and 10. This is 20 and multiplied by zero point 0.2 is zero point 0.4. So this is 20 and sand only. So you see at somewhere around 38%, you get much higher packing density as compared to 20 and 10, right? And if you see 10 and sand, if you see, it will be less than this. 20, 10 and sand will be less than this. Just 20 and sand gave a much higher particle packing than 20 and zero point 0.2. With 20 just 2.36 aggregates, mixing of that, and that gave even a higher particle packing, and so on. So this is basically the the theory that gap grading materials give you much better particle packing, and that is because of the myth. That is because the myth is not true, that the void sizes between the aggregates are half that size. It is much less than half the size of these aggregates. And what he did was he did a study with natural aggregates again. So beta 1 is the particle packing, the void content or the packing density of these each aggregate. Now it could be the same size of aggregate, 20 and 20 on both the sides. You are having 20 of both same size aggregates, but sorry, beta 1 is the particle packing of the aggregate which is smaller in size, or the other as compared to the standard one. So lesser particle packing means the aggregate is flaky. Higher particle packing means aggregate is lesser flaky, and the highest particle packing is not flaky at all. It is either spherical or cubical in shape, a good shape. So when you're mixing this flaky aggregate and a normal aggregate, a good aggregate, you see the flaky aggregate, even at the highest packing density, will be much less than the mixture of aggregates with good particle packing. So first thing that is affecting the particle packing is the proportion of the sizes of these aggregates that you are mixing together. The second thing is the packing density of the material, the quality of the shape of those materials that you are using for packing these aggregates together or mixing these aggregates together. And the reason this works is because of two effects called the loosening effect and the wall effect. This wall effect is not necessarily closer to the cube surface, the cube wall, or the structure, the form work. It can be even true against the bigger aggregate size. So wall effect is, let us say, if the aggregate was not here, there could have been another, smaller aggregate that could have come over here, where the aggregate wall effect is written. Since this aggregate has come here, this point is with void. This point is with void because this wall has come, and this aggregate, because it is not able to fit between this in this small thing, it pushes away. And this is called the wall effect. This happens near bigger size of aggregates. This happens because near the structure, the form work. And the second thing is the loosening effect. So loosening effect is where you put aggregates just the half the size of the aggregate which is bigger than this, and the void, the size of the void, basically it increases a little. And instead of getting better particle packing, you tend to get lesser particle packing. A good effect would happen when the aggregates have a dilation effect. Dilation effect is if you put 20 aggregate in the cylinder, you put the other material just flows between the aggregates. If it is in loose condition, this material just goes inside these aggregates and flows. If you're putting the aggregate, it does not go inside the aggregate, means it is not dilation. You have to mix it together, and after mixing it together, then you'll get certain volume, and this volume will not be the same. It will be higher than the volume of the aggregate that was there initially. So when you're putting this effect of dilation happens only when you're putting much smaller particles. So for 20 if you put 10 it does not work. But for 20 if you're putting sand, the sand particles will easily flow between the aggregates and they will fill up the voids. You'll get much better effect. Now, this study is between the particle packing of rounded and crushed aggregate. So in normal words, I would say this rounded aggregate is nothing but river sand, and this square shaped graph, this is your crushed sand. So what he has done is he has separated particles of different sizes, and then he has found out the packing density. Now what he found out was the rounded aggregate for the same size of aggregate gives better packing density for higher sizes. For lower sizes, the difference between the particle packing is lesser. For lower sizes, the particle packing is almost the same. But for higher sizes, rounded aggregates give you better particle packing as compared to angular aggregates. Now, the reason I have given you the explanation for aggregates, even though I'm speaking about ultrafine minerals, is because whatever is true for aggregate is actually true for the fine materials. When you're using cement with a very low water cement ratio, when you're making concrete with a very low water cement ratio, and the cement is not hydrating fully, there are many high chances that there would be voids left behind, the capillary pores left behind the cement particles. These voids tend to give lesser strength, and somehow, even though the strength that you measure may be 70 MPa, 60 MPa, the reason the strength is not even more is because even after hydration, when the cement particle has grown in size, between these hydrated cement particles there are voids which are much more weaker than the hydrated cement gel. and these voids need to be filled. So here comes the role of ultrafine minerals, where the packing starts happening and you get a denser matrix, where the cracks will not be able to pass through these voids, and you will tend to get even more higher strength. Now, how do you proportion these concretes? So, you have got, as per IS 10262, the new one, you have got now three curves for different water cement ratios and strengths: 33, 43, 53. But what happens when you put ultrafine materials? For the same water cement ratio, if you are using ultrafine minerals, you get higher strength. Um, so, let us say with just OPC, for zero point 0.5 water cement ratio, you get 20 MPa or 25 MPa. If you incorporate ultrafine, if you replace some ultrafine minerals, if you replace cement with ultrafine minerals, for the same water cement ratio of 0.5, instead of 25, you may get 30 MPa strength. And this happens for all the water cement ratios. So how do you actually do it? The best method for proportioning concretes with ultrafine minerals is not the IS method or ACI method or DOE method. The best method is the BRMCA method. And many of us would have come across this BRMCA method. Some people call it family of mixes method. BRMCA stands for British Ready Mix Concrete Association. So family of mixes method, wherein you don't first, decide what is the strength is going to be. Basically, as per IS code, what we do is we say, if you want M30, this much water cement ratio, itna water cement ratio लो, trial डाल दो, itna strength आ जाएगा. And the strength usually comes somewhere around 41, 42, or instead of 38, it comes 35. हाँ चलो चलो इसमें थोड़ा सा strength cement बढ़ा लेंगे. Let us start supplying concrete. So that is not the correct method. The BRMCA method works the other way around. It says, don't decide the strength of concrete initially. Just do the trial with different cement contents. They don't go with water cement ratio. They say with 300 kg cement, do a trial, 350, 400, 450, 500, and measure these strengths. Plot a graph of cement content versus the strength that you get, and interpolate whatever strength you want based on this graph, and find out the cement content. That is BRMCA method. And also we have developed nomograph for calculating the strength of concrete for the replacement of ultrafine minerals. So this is the BRMCA method. You see, this is how you do the BRMCA method, the family of mixes method. You uh, do trials with different cement contents, okay, with the same water content. So you get a different strengths, and these different strengths, plot a graph. So if you want a strength of 25 MPa, just plot a line from 25 till this graph, and then plot a line down. You will come to know that, okay, for getting a 25 MPa strength, I require a cement content of somewhere around 220 kgs. This is how the BRMCA method works. This is the most accurate method. And many people, who don't know this, when I say itna cement content mein itna strength aayega, they actually start laughing, because people think that only this method of IS method is the correct method. That is the theoretical method. Practical method is BRMCA method. So this is what we have tried to do with the water cement ratio, the BRMCA method. We have gone a step ahead. The BRMCA method, in fact, this graph is with respect to the water cement ratio and the strength. So this is what happens with water cement ratio and strength for different percentages of ultrafine: 0%, 1%, 2%, and so on. So at 0.39 water cement ratio, let us say you get 27 MPa, and if you incorporate 1% ultrafine as a replacement of cementitious matrix, you tend to get 2 MPa higher. Then at 2%, you get even higher. And this is how we have actually been able to plot the strength. Uh, so this is what I meant by this. Or what happens is, if you want the same strength, let us say if you want 23 MPa strength, so 23 MPa strength without ultrafine, you would require a water cement ratio of 0.48. But if you incorporate, let us say, 2% of ultrafine, you can get the same strength at 0.53 water cement ratio. So you can use ultrafine to do either of these things. And that is the reason why you tend to get better rheology. One thing, let me uh, clarify that if you keep the same mix and just replace the cementitious with ultrafine, don't expect that you will get lesser stickiness. You will get lesser stickiness for the same strength when you are able to change the water cement ratio, when you're able to change the mix, when you're able to make the use of the ultrafine properties, the property of ultrafine minerals. If you're able to use, if you're able to utilize those properties, then you will tend to get better mix with better workability, better pumpability, and better strengths. You need to know how it behaves, and based on that you do your mix. Now, one more thing that happens with ultrafine minerals is, let us say you did a water cement ratio 0.44 and you got a strength of 24 MPa, right, as per this graph. Now, if you want to use the same water cement ratio, 0.44 water cement ratio, and you want to increase the strength, basically you want to increase the strength. So what you do is you incorporate percentage, let us say 4% of ultrafine. You will definitely get higher strength provided you do admixture reformulation. Because as you keep on going at a higher and higher level of ultrafine, it starts behaving like a lower water cement ratio concrete. Because basically for the same, let us say without ultrafine, you yourself, when you reduce the water cement ratio, you change your admixture. You always change the admixture. You have got mid PC, low PC, high PC. The reason you have got high PC for higher strength is because the water cement ratio is lower. You get higher strengths over there. So don't shy away, because what will happen is, if you are making a concrete without ultrafine at point, let us say at 0.49 water cement ratio, and then at 0.49 water cement ratio you want to use 5% ultrafine, that means at this point you will need to reformulate your admixture. You may need to go with a high end PC, right, because these materials are much more finer than cement particle. You require a higher effort for dispersing them. Now this is the nomograph that we have made for designing the concrete with ultrafine. So as I told you, this left hand side of this graph is the same equation that I had shown you earlier. It is the same equation uh, that I've published in my book. So the same equation for different strengths of cement. Now at 0.43 water cement ratio, let us say you get a strength of 32 MPa. How do you use this nomograph? Let us say you have got your data, your trials data, you have got at 0.43 water cement ratio. You do the trial and you are getting a strength of 32 MPa. So your graph is actually the green one. Your current materials are behaving like the green one. And now instead of 30 MPa, you want to increase the strength to maybe 30. What you do is, from the same point 30 at 0.43 water cement ratio, you plot a line till you come across 38 MPa or whatever strength you want. The point where this intersects is the line of percentage of ultrafine that you need to use. So at 0.43 water cement ratio and 3% ultrafine with the same set of materials, instead of 32 MPa, you will end up getting 37, 38 MPa. And if you want a higher strength at the same water cement ratio, you can go with higher percentage of ultrafine. And mind you, you will require, it may be required that you may need to change the admixture or reformulate the admixture. Now, what are the advantages of ultrafine based mixes? So first is you get better material, I mean lesser water demand as compared to any other microsilica also. If you have chosen, till today, many of us were using concrete, higher strength concrete, only using microsilica. But now many other materials have come, ultrafine slag, ultrafine fly ash, wherein you can incorporate uh, this material at a better advantage if you understand. If you remember the graph, when the finer particles were there, for bigger particles, the packing was better. But as the particle sizes kept on reducing, the packing reduces. Finer particles are good only if they are used to fill between the gaps. But if the gaps are much bigger and the particles are much smaller than the gaps between the bigger size aggregates or bigger size cement particles, then this will actually create disadvantage. So it should be not too fine, but it should be just fine, so that you are able to get the good type of workability and type of strength. Here you also get much better strength at 24 hours, better workability and slump retention, lower heat of hydration, and a good strength of concrete. It has got a better sulfate to resistance to sulfate attack, reduced chloride penetration and migration test. Now, one thing, let me clarify you. Uh, uh, One government body in Mumbai has now actually migrated from rapid chloride penetration test, RCPT test, to RCMT test, rapid chloride migration test. The reason being, RCPT was a kind of a wrong test because it was also measuring the current that flows through concrete. So, for example, you have got a concrete in this RCPT test assembly, and you are passing the current through the solutions of sodium hydroxide and sodium chloride. Now, the assumption was that when the chlorides move across the concrete, the current flow will be higher. Absolutely fine. But this current flow is so higher if you are incorporating steel fibers. Let us say if you put steel fiber in the concrete, the steel fiber will start conducting current and you will start getting higher coulombs, even though the concrete is not allowing the chlorides to flow through. Or even if you're not using steel, let us say if you're using carbon, nanocarbon, or carbon particles, okay, or graphene or nanocarbon tubes. Nanocarbon is also a good conductor of electricity, or any carbon particle is a good conductor of electricity. So if you got carbon particles, because of some reason or the other, flash particles have got unburnt coal particles. From some way or the other, you are getting carbon particles inside the concrete. That also will lead to increase in current. And RCMT test, migration test, what it does is, there is a mathematical calculation that you are supposed to do after doing the same test. You are supposed to, like the same RCPT test, almost same. You are supposed to bring out the concrete sample, break the concrete sample, and on the fractured surface, spray silver nitrate solution. And what will happen is, till the depth the chloride has actually penetrated inside the concrete, till that depth the color will turn into white, because silver chloride is white in color. And you will have to measure that depth, calculate the average, plug that value in the formula along with the current. Then you will get a better understanding about the concrete durability and its capacity, or how it migrates the chloride. And this Mumbai, the government body that incorporated RCMT, they gave a value of 2 into 10 to the power minus 12. This was the value required for the concrete. And trust me, they were not able to get that value in 28 days, no matter they used what material. The only way to do this is use ultrafine minerals, and we have been able to get at 28 days much less than 2. We have got somewhere around 1. In some case we have got 0.7 into 10 to the power minus 12 per meter square, that kind of value for RCMT. And this is how you can incorporate these materials, to get much better performance. If you see, these are some of the reference microsilica mix and ultrafine mix. This is the retention. You get much better retention in ultrafine mix. The blue one is the ultrafine. The gray one is the microsilica mix. This is the strength with respect to the control. These are the actual strength at 7 and 28 days. This is the RCPT test. Now, not just RCMT, even in RCPT test, you get much better performance when you incorporate ultrafine. These are the results from the third party structural, right? So just the magnified view of this. So the RCPT values that we have been able to get is 645. This is the heat of hydration test that we have done. Now this is not for the same mix. This is for the same strength at 28 days. So the mix is different for both these graphs. This is the control mix without ultrafine. This is mixed with ultrafine for same strength at 3% ultrafine. And you see the temperature is much less as compared to control concrete. Now some case studies. This is the bullet train project trial that we did. Their requirement was M50 for pre-stressed concrete, and uh, in one day for M50 grade concrete, they have been able to get with our material 39.05 MP ultrafine minerals. At 3 days for M50 grade, they have got average of 48.28 MPa, right? Which was much less as compared to, the microsilica that they were using earlier. And they also were kind enough to allow us to reproduce this sheet of theirs. And at 7 days for M50, they have got almost very close to the target strength, 57.36. And this is what from their register we have been able to get at different days. So at 14 days they've got 57, again almost the same. 21 days 66, and 28 days 68 for an M50 grade of concrete. Now mind you, this strength was in addition to a higher workability as compared to their current mix. They were facing a lot of challenges in terms of bug holes in the sections that they were casting for M50 grade concrete for the bullet train, that girders that they were casting. So they used to get a lot of cracks, also because it was a mass concrete, and microsilica being very sticky, because it is, densified material. You require a lot of admixture to disperse it, and even after you have dispersed, the mix remains sticky, and also because it is much finer as compared to ultrafine. So these materials, have been able to give much higher strength with better workability and pumpability. Now, this, I'm sorry, this the name has got, it's hidden, because I just copied and pasted from other slide. I did not realize that the name has got hidden. This is Tata Projects M30 Ujjain, and they wanted a concrete design where the strength would be enough to open the traffic within one day. And this was M30 grade of concrete for M20. This was M20 grade of concrete. So one day they wanted more than 20 MPa for the traffic to open, and we incorporated 5% of ultrafine, and you see the entire mix. And they also they allowed us to reproduce this mix. And you see, with just one day strength, incorporating 5% ultrafine, they've been able to get 26 MPa for M20 grade of concrete. At 3 days, 31, and so on. Now, this is another case study for from Gujarat, where they have used ultrafine GGBS along with the cement and fly ash, and they did this for for reducing their cost of concrete. So if you see M25, M30, and M35, so this was a research work also. So they filled the cubes initially. They filled cubes after 1 hour. They filled cubes after 2 hours, and they did the same thing for all the other things. So if you see, the strength that they get is higher for later age in all the cases. Initial concrete strength is much lesser. So this is something beyond the ultrafine scope. So this is something, the effect of mixing. The more amount of mixing gives you higher strength. So many people say that, Are, initial strength you'll get higher. No, initial strength you'll get lesser, but if you mix it for a longer time, you tend to get higher strength. And this is because the energy that you put in the mix to disperse the cement particles, so that all the cement particles hydrate, you definitely get higher strength for higher amount of mixing. Of course, this is the average that they got. They've calculated the average. But you see, this is how, they have significantly been able to see that the strength is higher for higher amount of mixing time. This is a JMC project for M60 grid of concrete in Bangalore. They have been able to get 58 MPa in 7 days. This is another case from Gujarat. So you see, the top mix, the 7 days. So here they have been able to save a cost of 100 rupees per cubic meter to get the same strength for M25 and M30. And if you see, the strengths are almost the same. They have been able to get the required strength with, even though the cost of concrete has reduced by 100 rupees per cubic meter. This is from Skyway Central Lab for their concrete that they supply for Metro, Mumbai Metro. And if you see, this is without ultrafine. They get a strength of 23 MPa in 3 days and 28 MPa or 29 MPa in 7 days without ultrafine. And the cement content is 380 kgs. Now, if you see, with ultrafine, the cement content was reduced to 300 kgs and ultrafine was incorporated of 25 kg, and they have been able to get 31 MPa in 7 days and 23 MPa in 3 days, almost the similar strength or better strength, not similar but better strength. But I would be rather humble and call it the same strength. Now, this is a very interesting case. In Mumbai, an engineering college came up with a competition of the highest strength to weight ratio. They gave out this competition to all the colleges, and all the colleges participated. One college from Mumbai, Terna Engineering College, they came to us. The professor is known to me, and she asked me for help. And we said, yes, surely we'll help. Why don't you use ultrafine? You will get much better results. There were two teams from their college, and both the teams won the first and second prize. And these teams have come to thank us, our team, for helping them. And they came with bouquet flowers. So their numbers that they got was 13. The strength to weight ratio that they got was 13 for the first group, and the second group got 12, something 12 point something. The third, the third group, which was from some other college, they were getting 5, 4, that kind of strength to weight ratio. So you see, even incorporating ultrafine, you can get this kind of benefits. And basically, engineering, if you see in design, the main challenge is strength to weight ratio. The same material, the biggest load for any structure is its own load, is its own weight. So when you're able to make a concrete with a higher strength to weight ratio, the structure will become more and more efficient. You will be able to make more structure out of the same structure, same materials. So that is it from my side. Over to you.
Yeah, thank you, sir. It was a great presentation. So I would now request our chairman, Nirmalendu Kargupta, sir, to please put your views, sir. Kargupta, sir. Kargupta, sir,
Yeah,
are you there?
yeah. Yeah, good evening, all.
Yeah.
Good evening, sir.
Uh, it was a nice presentation. The concept of water cement ratio is there. Concept of aggregate cement ratio is there. Particle packing is there. And how particle packing interfering the, plastic viscosity and yield stress, what is called rheology. It is also there. And how the finer particles and intermediate size particles affecting the strength, it is also there. It is a nice presentation. So I always request all the participants, if you have any questions, so you can ask right now. Fantastic, sir, for your report. Would like to thank you very much that you have come to our show, and you have explained very nicely. Thank you.
Thank you for inviting. Rather, I would say thank you for inviting me.
Any questions?
I think there are questions in the chat.
Chat box, we requested myself and yeah. One question is from Saurabh Sharma. Sir, can UGGVS, ultrafine GGVS, okay, replace the integral waterproofing compound for making structure watertight? Second is ultrafine GGVS having hydrophobicity and pore blocking properties as crystalline waterproofing compound is having. So
Wow, that's a very fantastic question. Uh, Waterproofing, basically, it may have waterproofing, but it will not be used because you see, when you're making concrete with a higher water cement ratio, which is enough for getting the structural strength that you require. So let us say M20 grade. Uh, so M20 grade basically is a very weak material, uh, where the water cement ratio is much higher. If you take a M20 concrete with or without ultrafine and M80 concrete with or without ultrafine, you keep these cubes in curing tank for 28 days. When you break it, you will always see that M20 grade of concrete, even after breaking the concrete inside the cube is wet. The reason is, the even though the structure is porous, that much porosity is enough to get the required strength for the set of materials. But for M80 grade of concrete, when the water cement ratio is low, very low, you know, the particles are very close to each other and they are able to block. The only thing that ultrafine can make the concrete watertight is at a water cement ratio a little low, a little higher than the normal concrete. So let us say a normal concrete will become watertight at, let us say, a low water cement ratio of 0.25. So with ultrafine, it may so happen that the same concrete can become watertight. Instead of 0.25, it can become watertight at 0.27 if it is watertight, right? But even though you know M80 grade concretes, if you see, they are watertight, they do not allow the water to pass through. You can never replace waterproofing with the grade of concrete, because it's not only the material or the concrete quality that will stop the water leakage, it is the workmanship. There are many factors in workmanship. Even though the concrete material is good, the biggest challenge is the workmanship. you know uh, there are thousands of people who are working at the site. There are thousands of places the site is the same, the work is going parallelly. It is very difficult, and the quality of people available is not so good. So you cannot leave things to the on the mercy of the people that they are there. So workmanship is the main reason why waterproofing is still needed. Even though if you are able to make concrete without which is watertight, even though if you're able to make, you will require waterproofing. Waterproofing is another level of safety. And waterproofing also, if you see many waterproofing people who do waterproofing, they themselves use 3 or 4 different layers of waterproofing. They first do coating, on that they put coba, on that they put something else. So they themselves are not relying on just one thing. They are doing 2 3 things, because if one thing fails, the second thing is there to stop it. So even though the ultrafine material can help in making concrete watertight, I do not recommend means not doing skipping waterproofing part. And ultrafine GGBS, no, it has not got any hydrophobicity. It is not like the crystalline waterproofing. Crystalline waterproofing is a totally different ball game. It is more exaggerated version. I understand why you're saying this, but it is a more exaggerated version of ultrafine GGBS or GGBS or flash. Flash and GGBS also have got that property of autogeneous healing. When cracks are formed and the water is in constant touch, the flash also leads to slow, very, very slow repair, or slag also they have found. But crystalline waterproofing, as they claim, I have not tested it myself, but as they claim, and if I understand, it is much more, it is a more exaggerated version of self-healing. Right. I hope I have answered your question.
Yes,
Yeah.
sir. Thanks a lot, sir.
Manju M, sir, OPC plus PFA GGBS is okay. PPC plus PFA plus ultrafine, how is working? PPC, PFA, and ultrafine. He's
Wow,
asking.
that's a very good question, and thanks for asking it. So the first thing, even if I give the answer, the first people will say, सर आईएस कोड में तो नहीं लिखा है कि फ्लाई एश 35% के ऊपर इस्तेमाल कर सकते हैं. अगर पीपीसी में पहले से ही 35% है, हाउ कैन आई पुट मोर फ्लाई एश, राइट? So there have been cases where fly ash has been used 50%, 60%, and for government projects where government people also were not, they, uh, even though it was written in the IS code, they were not able to negate whatever was being said by the contractor or the concrete supplier. So fly ash, if you read, again, it is the interpretation of the IS code. If you read the IS code, it says fly ash should not be used more than 35% as a replacement of cement. But it means that if you want to replace fine aggregate, you can use beyond that. So if you're using PPC plus fly ash plus ultrafine, yes, it will work very well. You will get much better results. And trust me, for many other properties, since I'm from RDC, we have got certain, um knowledge rights or some intellectual properties which I cannot tell over here. But yes, you will surely get much better results in PPC plus PFA plus ultrafine, or OPC plus fly ash plus slag. Not for all the aspects of concrete. For durability, if you are measuring at some point, for some parameter, you get much better results. It may not be for strength, it may not be for economy, it may not be for durability, but something, one thing out of these things, that you will get exceptionally good result.
Thank you, sir. The next question is from Shubhankar Khara. If we use ultrafine material during cement production, will it help? He's
Yes,
trying to blend ultrafine along with clinkers.
yes, it will surely help. But ultrafine, is made by expense of energy. You need to, like ultrafine slag, you need to expend a lot of energy in grinding it to a very higher fineness, almost 10 times finer than the normal cement particle. And also, if you are saying ultrafine fly ash, there also the expenditure of energy is very high in classifying. First transporting the fly ash from the from the fly ash source, and then classifying the fly ash is expense of lot of energy. Cement is something which is not a tailor-made product as of now. People buy cement as a raw material and then they tailor make it for whatever performance they want. They can add fly ash into it, they can add slag into it. So let us say if you want some different kind of property which OPC is not able to get, you will add fly ash. Or let us say if you want high early strength, if you don't want later age strength, you don't want durability, you want 3 day strength. In that case, you- adding no fly ash or slag is a very good option, right? Putting only fly ash. So similarly, so that's the reason why having OPC plus fly ash at the plant, I'm totally against. I'm totally against the PPC policy as a country, as a country, where economy is, everything is available at the most efficient price. So in that case, the least energy that you can expend is buying OPC and fly ash and mixing it together, rather than buying mixed fly ash, because the cost of transporting fly ash from the thermal power plant to the cement plant and then bring it back to the market, there is an extra cost of transporting the fly ash from the thermal power plant to the cement plant, right? So that it becomes expensive. So it is always better to use OPC and fly ash. Exactly on the same thing, I would recommend not putting, I mean, for the nation, if at all this is going to happen, if this has to be decided, adding ultrafine into cement is not, even though it may be a good product, it may become a better product, but it may not be an efficient product. It is better to use OPC and ultrafine separately, because you will be having the right, you will be having the freedom to tweak the product as per your requirement. You don't know what percentage of ultrafine, what percentage of fly ash is good for your requirement. At the same project, it could be that you will be requiring high early strength, and also another concrete where you require higher durability. And for these two, both these mixes, you require totally different mixes, right?
The next question is from Suvendu Patra, sir. Can we use higher replacement of ultrafine GGBS for high grade concrete?
Yes, definitely, and that is the good way to do. But as I told you, when you go for higher percentage of ultrafine, you need a higher and stronger admixture. Um, and that is where you will end up, facing a problem when you're putting higher percentage of ultrafine. Definitely, it will help, but with that, you require a good admixture, a very strong admixture.
Next question. Could carbon black from Suvankar Khara? Could carbon black be good material as ultrafine material as it floats during mixing of water?
Uh, yes. So carbon black, another form of carbon black is graphene or carbon nanotubes. Uh, they are being used in concrete, and they are being used for advantage. So carbon black is basically a very big particle of carbon, and that actually creates problem, because when you are using carbon nanotube, the quantity of carbon nanotube per cubic meter of concrete is less than one particle or two, three particles of carbon black, which is much bigger in size. So uh, if you see the percentage of nanocarbon tube or graphene is very, very less in 1 cubic meter of concrete, and that gives you better flexural strength, or higher modulus of rupture, and also a higher toughness when you're using carbon nanotube. But carbon black, and when you go beyond, if you even if you're using carbon nanotube or graphene beyond a certain percentage, the concrete, you will not be able to make the concrete. The workability you won't be able to achieve no matter which admixture you use. It is because this innate property of carbon to absorb or suck the admixture, leads to a lot of problems in concrete workability. So same problem happens with carbon black. Carbon black, since the size is very big, it absorbs the admixture and water, and you get much lesser workability. That's why carbon black may not be good. But carbon nanotubes or graphene can surely help.
Next question from Muhammad Atar Hussain. He's saying, does incorporating MCI admixture will affect the RCPT values?
What is MCI? I'm not able to understand. If Muhammad Atar can please unmute and tell what is.
I think it is migratory corrosion inhibitor. Maybe.
Okay, migratory corrosion. I would frankly tell I don't know about this. Yes, there are, in my previous organization, people have done study on this, and it does reduce the chloride penetration. The study that my colleagues did in my previous organization was not on the RCPT test, but it was for corrosion. They were actually monitoring the corrosion of concrete inside of reinforcement inside the concrete. And I don't remember the ASTM number, but there is a good test, and it takes a good amount of time. It takes almost 6 months. So with that, they were getting good results. But I think there are much better options as compared to MCI admixtures. MCI is, maybe you can treat it as one level of security, and there could be another level of security. So 2-3 things is what would give you better results.
I think this is the last question, or what is? Venkat Krishna Reddy is saying 450 plus 200 plus 50 OPC, 450 OPC, 200 GGBS and 50 ultrafine. Is it a good combination in factors of high CaO, calcium oxide?
I'm sorry, I didn't get this question.
Venkat, can you say something about your questions? High calcium oxide means? Venkat Reddy is there? Okay, we can shift to next questions. Lalit Kele. If we are using ultrafine percentage in mix, need to increase mixing time while batching?
May not be required. But if you are going beyond certain percentage, let us say very high percentage, I would mean above 5%. Yes, in that case, mixing time may increase. Or if you want to reduce the mixing time, a good admixture is what will reduce the mixing time. And also the water cement ratio. If you're using higher percentage of ultrafine and the water cement ratio is 0.5, obviously you don't require much mixing time. But let us say the water cement ratio is 0.2 and the percentage of ultrafine is 6-7%. Definitely you will need a higher mixing time.
I think we have ended our questions sessions.
Yes.
Would request Mr. Ramanjit to give vote of thanks and
Thank you, sir. Today with us, Sanjay Gupta ji is there. So I would request him to
okay.
give vote of thanks. But prior to that, I would like to show a presentation about concrete engineers. So I'll take just 2 minutes. So is my screen visible?
Yeah.
So about concrete engineers, sir, we established concrete engineers in the year 2018, and this is our 23rd webinar, Tech Talk with by concrete engineers, and we are conducting seminars, workshops, and site visits also. We are conducting, and how you can be a part of concrete engineers. So you can WhatsApp us on this number 7678319777, or you can mail us on concreteengineersnewdelhi@gmail.com or admin@concreteengineers.org. So this is a small like. And now I would request Sanjay sir to please propose the vote of thanks.
Sure.
Sanjay sir.
Yeah, please. Thank you, sir. On behalf of concrete engineers, I would like to thank Engineer Avijit Chaubey sir by delivering such a wonderful presentation on concrete mix proportioning on high performance concrete by using ultrafines. In this presentation, we have explained a lot of things, and we have learned about how to use RCMT versus RCMT test versus RCPT test, importance of mixed rheology, and many more things. You have also explained the how to use nomograph by calculating the exact percentage of ultrafine. So by which we can design mix in a proper way by proper maintaining rheology of mix. So all information is very useful for us, and I sure all participant has benefited for your presentation. You have also explained the importance of BRMC mix design. as per your presentation, BRMC mixed design is method is very useful, by which we can calculate the exact percentage of all ingredients, and better and economic mixed design we can achieve. So overall, we again would like to thank चौबे साहब. बहुत अच्छा प्रेजेंटेशन रहा, सबने को बहुत एंजॉय किया. और इंजीनियर रमनजीत वालिया, निर्मलेंदु गुप्ता साहब, सभी हम लोग मिलके आपको अगेन थैंक्स बोल रहे हैं. और हम इस तरह की टेक टॉक कंटिन्यू आगे करते रहेंगे, और फ्यूचर में आपसे एक्सपेक्ट करेंगे कि और इससे अच्छी प्रेजेंटेशन हम लोग आपसे लें और सीखें सारी चीजें. थैंक यू. थैंक्स अ लॉट.
Thank you so much. Pleasure is mine.
Thank you, Sanjay Saab, and thank you all the participants. You have spared your valuable time, or you are keeping visiting our this webinars and all. आगे भी हम ये करते रहेंगे, and all these webinars are recorded and they are posted on our YouTube channel. That is also Concrete Engineers. You can view the webinar on that YouTube channel also. So thank you, sir. Thank you. Thanks a lot.
Thank you. Thank you, sir.
Thanks a lot.
Thank you.